Today's topic is using Bootstrap to build confidence intervals for a parameter that we want to estimate. I'm going to divide this into 4 videos. In this first video, I'm just going to quickly recap what we did last class and then introduce our example that we'll use throughout the day. And then we'll actually introduce Bootstrap confidence intervals over the next few videos. So the idea from last class is that we introduced the bootstrap as a way to approximate a sampling distribution of either an estimator or a pivotal quantity. And mainly we talked about this in the context of estimators. So there our algorithm had like 2 main steps. First step, for b equals 1 to capital B, where capital B is the number of bootstrap samples we're going to take. We take a bootstrap sample, and this is a sample drawn with replacement from the observed sample data. And then based on that bootstrap sample, we calculate a value of the estimator. So a specific estimate, a numeric value, theta hat B. And so by repeating this many times, capital B in our examples was 10,000, we obtain many different samples, theta hat B, from the distribution of the random variable theta hat. And this lets us get a sense of what the sampling distribution of theta hat looks like. So in our notation, theta is going to be the unknown parameter that we're trying to estimate. Theta hat is an estimate based on our original sample. And then theta hat subscript B is the estimate from a particular bootstrap sample, which I'll sometimes call a bootstrap resample. And one of the main pictures that we had last class was this pair of pictures where we compared 2 different approximations to the sampling distribution of the sample mean in a particular example. And so the first one was obtained by taking many different samples from the population and calculating the mean, the sample mean, based on each of those samples and then making a histogram of the results. And this is like almost the actual sampling distribution of the sample mean as an estimator of the population mean. The reason I say it's almost the exact sampling distribution is because it is an approximation in the sense that we have not like formally calculated an integral, which implicitly says sort of look at every possible sample that you might have obtained of size n equals 30. So this is really a sort of a Monte Carlo integration approximation to that sampling distribution obtained by drawing samples from the population. But it gives us the main characteristics. And so if we look at this top plot, we're seeing that that sampling distribution is centered around the population mean. It's skewed to the left a little bit, and it has some standard deviation that is maybe like around a half or so. I guess we would call that standard deviation a standard error of the mean. So that's our real sampling distribution, the distribution that we would really want to use in order to build a confidence interval, for example. The bootstrap procedure is a way to approximate that sampling distribution, and we obtain this bootstrap estimate of the sampling distribution by repeatedly sampling with replacement from our original sample. So here's the histogram showing those sample means from 10,000 bootstrap samples. And we said that it has the same general characteristics as the actual sampling distribution in terms of spread and shape, but it's different in terms of location. And so where the actual sampling distribution is centered at the population mean, the bootstrap distribution, the bootstrap approximation to that sampling distribution is centered at the sample mean, the mean of our original data sample. The reason for this is that in the bootstrap procedure, our original sample plays the role of a population. So any relationship between the actual sampling distribution and the population mean is the same as the relationship between a bootstrap sampling distribution and a sample mean. So I think that's all that I had to say there. And like I said, mostly we talked about the idea of the bootstrap in the context of an estimator, but it can be equally applied to a pivotal quantity, and things are a little bit nicer when you apply it to pivotal quantity, actually. So suppose that we're interested in a pivotal quantity t, and there are lots of possible pivotal quantities, but I think it's helpful to have in mind a t statistic. So for example, maybe we're thinking about t is equal to the estimator theta hat minus the true parameter theta over the estimated standard error of theta hat. This is our most commonly used pivotal quantity in a variety of settings. So capital T is this pivotal quantity. It's a random variable because both theta hat, the estimator in the numerator, is a random variable. It'll depend on my sample data x1 through xn. But also in general, the estimated standard error will depend on my sample data. For example, if I'm thinking about theta hat being the sample mean, x bar, then that depends on the sample data. And then this estimated standard error of theta hat is going to be sum I equals 1 to n of xi minus x bar over n minus 1, and all of that square rooted, so to the power of 1/2. So this is just one example, and we're seeing that in that expression for the pivotal quantity, their randomness shows up both in the numerator in theta hat, where there's x's, and in the estimated standard error, where there are also x's. So capital T is a pivotal quantity, a random variable. Based on our observed sample, t, lowercase t, would be the value of the pivotal quantity for that observed sample. I'm going to note that this is, I don't know, there's something a little bit funny about this in the sense that we would not actually be able to calculate this pivotal quantity for most purposes because it involves theta. And theta is not a known number to us. So we can't really calculate t, but we can sort of imagine that there is a value, lowercase t, associated with our sample. And that would be the realized value of the pivotal quantity for that sample. All right. And t subscript b is going to be the value of the pivotal quantity based on bootstrap sample number b. So we talked, I guess this is just exactly analogous to the quantities that we just discussed on the previous page, theta hat, capital theta hat, lowercase theta hat, and lowercase theta hat subscript b, which were the estimator, the realized value of the estimator based on our original data, and the realized value of the estimator based on bootstrap sample number b. Okay, so the thing that's nice about pivotal quantities is that part of the definition of a pivotal quantity is that its distribution does not depend on unknown parameters like theta. And so this gets rid of this problem up here. So the reason that the actual sampling distribution is different from the bootstrap approximation to the sampling distribution is that they're centered in different locations. And the location corresponds to the parameter we're trying to estimate. So the problem here is that the distribution, the sampling distribution of the estimator depends on the unknown parameter theta. So this is why like the actual sampling distribution is different from the bootstrap approximation to the sampling distribution. Down here, the distribution of a pivotal quantity does not depend on unknown parameters like theta. And so that means that we won't have this problem where the bootstrap approximation to the sampling distribution is in the wrong place, because that sampling distribution is not allowed to depend on unknown parameters. So it's not going to move around based on whether I'm sampling from a population or a sample from that population. So to make this concrete, suppose that I'm thinking about this pivotal quantity, the t statistic, t equals x bar minus mu over standard error of x bar. Well, since x bar is an unbiased estimator of mu, the expected value of the numerator is 0. Expected value of x bar minus mu equals 0. So that means that the expected value of t is 0. So the mean of this distribution of t will always be 0, and the location of the distribution will not change depending on whether I'm looking at the actual sampling distribution or the bootstrap approximation to the sampling distribution. So the actual sampling distribution and the bootstrap approximation to it will both be centered at 0. So this is a nice thing about using a pivotal quantity, and it makes things, it means that we sort of have to worry less about characteristics of the bootstrap when we're basing things on pivotal quantities. All right, so I want to explore bootstrap confidence intervals in the context of the following example. So this is from the book Mathematical Statistics Based on Simulation or something like this by Hester Berg. So what we have is data on the amount of time that it took Verizon, the telephone company, to repair problems in their telephone lines in the state of New York. And so Verizon was actually sued and taken to court, and they were accused that they took longer to do repairs than they had promised to do in their legal contracts. And so I guess if we just look at the plot here, we have a plot that's a histogram of the repair times for different repairs that they made to problems with their phone lines. You can see that this distribution is very much skewed to the right. Ordinarily, if distribution was skewed to the right, I would not want to use a mean, right? I'd prefer a median or something like that as a measure of the typical repair time. But for legal reasons having to do with like what was written in the contracts, there was interest in estimating what the average repair time was. So our goal here is to get an estimate of the average repair time. And so I can really just get that by taking the mean of the times. And so this is 8.411611. So I think that's in units of days. So it took about, on average, 8 days to fix their problems. But now suppose that I want a confidence interval for this mean. Any usual confidence interval idea for the mean is going to not work because this distribution is so skewed that anything based on a normal distribution is just not going to be appropriate. So we need another approach to getting a confidence interval. And our sample size is moderately large. I forget how large, I didn't print it out. It's moderately large, but not large enough that I would necessarily feel comfortable about using a large sample normal approximation, particularly given how skewed this distribution is. So we're going to explore bootstrap confidence intervals for the mean repair time. And we're going to look at two approaches to doing this. There are a whole lot of bootstrap confidence interval procedures, like probably at least 40 or 50 different ideas. We're going to look at two of the most common, which are a bootstrap percentile approach and a bootstrap T approach. And for the bootstrap T, this is going to be based on the statistic that we've been talking about, or the pivotal quantity that we've been talking about, theta hat minus theta over standard error, estimated standard error of theta hat. And so in the denominator of this statistic, you've got a estimated standard error that you need in order to calculate that pivotal quantity. In this particular example, you have a formula for the standard error, and so we'll see that a little bit later on. But in some examples, you might not have a formula for the standard error. And so what you need to do in that case is get an estimated standard error using a second bootstrap. So we're going to have two variations on a bootstrap T confidence interval. One where you just have a formula for the standard error, and one where you need to do nested bootstraps to deal with that issue. So I'm going to stop this video here, and our next video will pick up with the bootstrap percentile interval method.